Hello and welcome to another session in physics. In this session we will be looking at the topic simple harmonic motion. But before that, let us review the previous lesson. Welcome back. Now let's look at the definition of simple harmonic motion. I'd like to let you understand that we've been discussing about motion in our previous lessons, and we said we have different kinds of motion. We talked about things like translational motion, which we said is movement of an object from point A to point B, and then we talked about oscillatory motion. We said another name for oscillatory motion is vibratory motion. We also talked about circular motion before we talked about random motion, where we saw Brownian motion. So these are the different kinds of motion we have. And then we want to talk about simple harmonic motion now. Now, simple harmonic motion is a little bit related, or in a very huge sense, it's related to oscillatory or vibratory motion. So just channel your mind towards that direction. So when we talk about simple harmonic motion, we are referring to the periodic motion of a body or a particle along a straight line, such that the acceleration of that body is directed towards a fixed point. So let's say, for instance, this is a ceiling or an overlying plank or a branch of a tree, and then a pivot or a rope is tied down, and on this rope is attached a big ball. Now somebody pulls this rope to this direction. What happens? It starts moving like this and like this. Eventually you'll find it here. So it moves like this, and then it comes back. This will keep happening. This to and fro motion will continue happening until finally it comes to rest in this equilibrium position in the middle here. This is what we call simple harmonic motion, the periodic motion of a body that is moving along a straight line, and it is directed towards a fixed point. Now, a particle that is undergoing simple harmonic motion will move to and fro, like we said, in a straight line under the influence of a force. This force is called a restoring force that tends to bring it back to its original position. It keeps moving to and fro and is always being directed and back to its equilibrium position until it finally comes to rest. We have many examples of simple harmonic motions. The first example is the loaded test tube in a liquid. The second example is the mass on a string, just like we showed you here, the mass on a string. And then we have the third example, the simple pendulum, which is what you're just looking at here. Alright, so we want to talk now about angular velocity. I'm sure you're used to the linear velocity, where we just have to say displacement over time. But this one is angular velocity. Angular velocity is velocity possessed by a body when that body is moving in concentric circles. When the body is moving at an angle, it possesses angular velocity. And when the body is moving with straight line or in a straight line motion, it possesses linear velocity or straight line velocity. Now, angular velocity is denoted by this symbol. This isn't the W you know in English language. This is called omega. This is omega. It's a Greek alphabet. Okay? Now, this angular velocity is given by the angle turned through the body by the time taken for this angle to turn. So, angle, of course, is represented by theta, and time is, of course, t. Now, the unit of measurement for angular velocity is radian per second. Radian per second. Of course, angles are measured in radians or degrees. So, radian per second is the unit for measuring angular velocity. Here, you can see a system of a body that is oscillating, and as the restoring force tends to bring it back to its original equilibrium position here. Now, for a body that is performing simple harmonic motion, we have some general equations that are given, such as this one you see here, and you see that y is equal to a sine wt and plus or minus kx. K is the phase constant, wt is called angular phase. WT is the angular phase. We'll look at that also in subsequent lessons too. Angular phase, this is omega, like I said, angular velocity, and T is our time as usual, while A is our amplitude. This is used to find problems or solve problems based on simple harmonic motion. This is a general equation. Now this is similar to the relation distance equal to uniform velocity times time for motion in a straight line. And then always remember that instead of having area this time around, we're looking at a radius since it is at an angle or probably moving in circular motion. Now the linear velocity at any point is a distance from the central point of x, and it is given by v equal to the angular velocity with the square root, and inside the square root we have the square of the amplitude and the square of the distance, and we'll have to find the difference between two of them. That is our second equation. After the general equation for simple harmonic motion was our first equation, equation 1. Now the minimum velocity Vm corresponds to the point at which x is equal to 0. That is the velocity at the central point or center of motion, and it is given by this equation as well. The angular velocity times the area, amplitude and the angular velocity times the radius. So A here is amplitude. First, we say that the maximum velocity of simple harmonic motion occurs at the center of motion, x equal to 0, while the minimum velocity occurs at the extreme position of motion, A. So let me go back to the previous slide. If this is A, B, C, and you're asked, out of A, B, C, at which point is the velocity maximum? The answer is B. The velocity is maximum at point B. At which point is velocity minimum? Velocity is minimum at point C and A respectively. That is what this equation is trying to help us understand. That velocity is maximum at the center where the distance is equal to 0, and that it is minimum at the extreme positions where motion is equal to A, and gives us the amplitude. And everything we try to explain is just what you're seeing here in the diagram. So at the end of this video, or at some point when you're free, you can go back and look at this diagram very well and seek to understand it. At this point the angle is equal to 0, but at here the angle is maximum, and here the angle is also maximum but in the negative direction. And at this point too, the velocity is maximum and the initial velocity is minimum. The kinetic energy here also is maximum, and the force too is maximum here as well. So take time to look at this very well, and then you would understand it better. Now, since force and displacement are involved, it follows that work and energy are also involved in simple harmonic motion, because work is simply a function of force times distance or displacement. So if force and displacement are involved, then work and energy too are also involved, since energy is the ability to do work. At any instant of the motion, the system may contain some energy as kinetic energy or potential energy, PE. And the total energy of the system is given by the sum of kinetic energy and potential energy for a body that is performing simple harmonic motion. At the same time, energy can be conserved and it may change form and may alternate between potential and kinetic energy. Now, when a mass is suspended from the end of a spring that is stretched vertically downwards and it is released, this body or this mass oscillates in a simple harmonic motion where it moves periodically to and fro until it comes to its point of equilibrium or rest position. During this motion, we have already said before that the force that tends to restore the spring back to its initial position is what we call a restoring force. Or we can also, when a spring is involved, it tries to restore the spring back to its elastic position. The force that does that in a spring is called elastic restoring force, and it is given by F equal to minus Ky, where K is the force constant of the spring. The total work, on the other hand, done in stretching the spring at a distance y is given by W equal to the average force times the displacement, and this is the equation half Ky times y, or half Ky squared. Now, what it simply means is that the maximum total energy that is stored in a spring is given by this equation 2, half Ka squared, where A is the amplitude or the maximum displacement from the equilibrium position. This maximum energy is conserved throughout the motion of the system. And the two equations you see here are the equations for discovering the total energy at any stage of oscillation of the mass. The constant is obtained from Hooke's law, in which F is equal to mg, or equal to Ke, force equal to the force constant times the extension. Alright, so this is an equation used for calculating the period of that body as it oscillates through the its position and moves to and fro. So we have T period equal to 2 pi over angular velocity, or T equal to 2 pi root m, where m is the mass of the body and K is the force constant. At this point, let us look at this example here on the screen and see how we can actually use it to find the solutions to the problems we are faced with. It says that a body of mass is suspended at the end of a spiral spring whose force constant is 0.4 Newton per meter, and this body is set into simple harmonic motion with amplitude 0.2 meters, and we're asked to calculate the period of the motion, the frequency, angular speed, the total energy, maximum velocity, and maximum acceleration. So let's start with the first one, where we're asked to calculate the period of the motion. Already we have our formula for calculating the period, which is 2 pi root m over K. That is the formula we're going to use, and it's simply going to give us 2 pi. Of course, we know pi is 3.142. The mass of the body is 0.02. We converted 20 grams to kilogram, and we divided by 0.4, which is the force constant, and we're going to have our period as 1.41 seconds. That's it for the first one. Now, for this second one, we are asked, this is A part of the question. For the B part of the question, we are asked to calculate the frequency of the motion, and the formula for frequency is F equal to 1 over T, which gives us 1 over the time, which is 1.41 seconds, and we have 0.71 hertz. That is the answer. For the C part of the question, we're asked to find the angular speed. The angular speed is found by calculating 2 pi f. In other words, 2 pi times the frequency, which is 0.71. So our angular speed is going to become 4.46 rad per second. You can see how the questions are interrelated with each other, and that for you to move progressively, you need to be able to get the answer to the previous one. Now, let's also find the total energy in the system. The total energy is given by half Ka squared. Half Ka squared. Now, this half Ka squared is equal to half 0.4, and this 0.4 is the force constant. You write it well. 0.4 force constant, and then the A, the amplitude, is 0.2 squared. So here we're going to have everything together will give us 0.08 joules, of course. And then we have the second to the last part of the question, which is the E part of the question. We're asked to calculate the maximum velocity of the motion. We are going to use this relation, half mv squared equal to half Ka squared, and we're going to try to make m squared the subject of the formula, where we have 0.008 times 2 over 0.8, and then Vm is going to be equal to 0.89 meters per second. Or alternatively, we can also say, we have V equal to angular velocity times the amplitude, and it's going to give us V equal to 4.46 squared times 0.2 equal to 3.98 meters per second squared. Either of them will serve as the answer to that question. What we did here was to find the maximum acceleration. Maximum acceleration, E part of the question. Sorry, F part of the question. We had to find the maximum acceleration here. So A, we just made A the subject of the formula. This was F. Yeah, both of them are the same. So we use this formula to find the acceleration, the maximum acceleration, whereas this one is the maximum velocity, Vm. Alright, so that is it. At your own time, you can still take the video back to understand exactly what it is that we did and take time to look at it very well. At this point, when we talk about forced vibrations and resonance, we are talking about vibrations that result from the action of an external periodic force on an oscillating body. That is what we call forced vibrations. You see, every body that vibrates, every object that vibrates, possesses a natural default frequency of vibration, and this is the frequency with which the object will oscillate when it is left undisturbed after being set into vibration. We have principles of the sounding board of a piano or the diaphragm of a loudspeaker, which is based on the phenomenon of forced vibrations. Now, when the frequency of a vibrating body coincides with the natural frequency of a system, we say that the system is set into vibration with a relatively large amplitude. This phenomenon is what we call resonance. Thank you for joining us in this lesson, and to refresh your memory on what we've just discussed, please take the test that will appear on your screen, and do have yourself a nice day.